Our next session will focus on the application and use of equipment outside of standard hazard monitoring systems for a facility's grain hazard monitoring program, including layers of protection, safeguards, and the concept of last line of defense. Jason Eardley is the Process Safety and Technology Lead for ADM Agricultural Services in Millie, based in Decatur, Illinois. He has worked in various roles for ADM for the past 25 years. He is also the chair of NGFA's Safety, Health, and Environmental Quality Committee. So with that, Jason, we look forward to your presentation this morning.
All right, thanks, Jess. Good morning, everybody. Good morning. This morning, critical safety devices, I'll get into the definition in a little bit, but essentially this morning what I want to talk about is some equipment that would be critical for our operations, but also some of it is maybe a little more philosophical and subjective on risk management, risk tolerance, and as organizations, what we feel is critical. So I've worked for ADM for quite a while. For a majority of the time, I worked in the personnel health and safety, I guess, although process safety and chemicals are part of that. I've always been kind of a simple person, though, and I like the idea that instead of having to do complicated, complex, multi-step interventions or protections to keep people from being injured, that it always would be great if there's just one thing or a couple of things that you could do that would just prevent it. And yesterday, there were a few, all the presentations were very good yesterday, and there were a couple of little threads I kind of noticed as people were going through. And one of them was in the HOP presentation, there was a couple in that, but one was the not if, but when, and his crane analogy, which I really liked, in that I think it's easy for us to focus on getting into details, getting into procedures, and all that's important, like he said, but can you have the one thing that will keep a catastrophe from happening, an injury from happening, or worse? And so that's a good way to think, I think. Not if, but when. And there was also cultural components through the various presentations. And though you might think on the surface that a critical safety device, you're talking about pieces of equipment, how does culture fit in? Well, I think the culture fits in then going into the maintenance portion, which I'll talk about in a bit. That, what is our culture of not just having particular pieces of equipment possibly that are required to keep catastrophes from happening, but do we maintain them? What happens if they don't work? Do we shut down? Do we keep running? That's cultural. And again, it goes to risk tolerance. What risk are we willing to tolerate? And finally, and I'll have a little bit on this too, is the dichotomy is not the right word, but some of these items that you will have in your facilities that I'll talk about, things like HAZMON that Jess mentioned, we've got regulatory legal requirements to have them. And there are other components that you might have, or devices that you might have in your facility that aren't required by law, but maybe your organization has determined that we just can't tolerate a risk in this particular operation, activity, whatever it is that we're doing, without this particular piece of equipment or system in place. So briefly, just kind of an overview of what I want to talk about here today. One is just risk. And then, I guess I should say, and I put in here my definition. I don't know that there's any sort of official definition by either regulatory agencies, consensus standard producing groups such as NFPA, that actually define what a critical safety device is. But I'm going to go through what generally ADM and what my opinion is on what that constitutes. I want to talk a little bit about layers of protection. One of the presentations yesterday, he had a slide with the Swiss cheese. I have that same slide too. You've probably seen all those. You have your various layers, your safeguards, your layers of protection, and for something to happen, it has to be able to pass through however many layers you've put in place, from initiation to whatever event those are protecting against. CSDs to maybe consider in your operations. I will warn you ahead of time that a lot of these, not a lot, but a number of them do get into, I know that we have probably some feed facilities in the group and some fertilizer and some other chemicals. Some of them do get into things like pressure vessels and certain potentially hazard activities, potentially dangerous processes that you may or may not have at your facility. Go through a few events, and most of them are actually ADM ones that have happened, that have are related to what we had determined would be critical safety devices, and for whatever reason didn't function as we had expected them to do, whether it be maintenance, whether it be somebody talked about jumpering out Hazmon yesterday, I think, things like that. I want to talk a smidge about inspection, testing, preventive maintenance to make sure that they function, and also impairments. What do you do? What should you do? And again, I'm not telling you what to do. I can tell you what I'm going to go over a little bit is how we handle it. If we have what we've identified as a CSD and it is impaired for whatever reason. So, I'll bet you didn't expect that somebody would talk about pornography this morning. Or maybe you did. If we were having this conference in Vegas, maybe that would be standard. But how does the way I see critical safety devices and pornography tie together? Years ago, in the US Supreme Court, there was a lawsuit about obscenity in a movie and whether or not what was in that movie constituted, art, or did it constitute pornography, obscene material. And there were dissenting opinions on the court, but the court justice, Potter Stewart, said, "I know it when I see it." What's the definition of pornography? I know it when I see it. So, how does that even relate here? Even though we have a definition within ADM of what a critical safety device is, it's not always easy to determine what they actually are. There is subjectivity, and it goes back to, I'm going to talk about risk tolerance here like I mentioned, and it does come into that. In some cases, there are things that are specifically necessary, have to be put in. In others, and we have a lot of them, there's not a legal requirement. DHAs aren't a CSD, but it's not a legal requirement. We've chosen to do it. We've felt that it falls in what we want to do to reduce risk. So there is subjectivity in that aspect of it. One location might say, we just can't tolerate running a piece of equipment without this. Another might say, our operational experience, our procedures, whatever, what have you, we've determined that it is. So, our definition. A critical safety device is an instrumentation, a control device, or a control system whose failure would contribute substantially to the release of hazardous materials or energy. And it must operate properly, and we require it to operate properly, be maintained to operate properly, to mitigate or prevent the consequences of a release. So in this case, you might think, well, that's chemicals, but it's really any energy. It could be mechanical, it could be motion, it could be the gravity of the load from the crane that falls to the ground. So essentially, it's anything that we have in place that prevents or mitigates the consequences of that happening. So what is the significance there? Well, in our little part of the world, if an identified CSD is not functional, that's a no-go. Somebody said yesterday, what's a no-go in your operation? When do you say, that's it, shut it down? For us, this is one of those criteria. And there's a couple of ways, I know I'm starting to sound like a broken record, on how we've determined what they are. So in this case, I don't know how great this Venn diagram really is, but on the left you have that we have legal requirements. This could also be the AHJ. that was mentioned yesterday, the authority having jurisdiction. So in this case, legal requirement for HAZMAT, dust collectors, the pressure differential monitoring. That's required, at least in the US, in 1910-272. So for us, even though that might not necessarily be something that one might think of as, well, if our magna helix down, is that dangerous? Well, maybe it is, maybe it isn't, but it is legally required. So for us, that would be considered, here's a CSD. This is a license to operate. This device must be functional for us to have a license to operate. Then on the right side, we have what we have determined as a group, as an organization, on, again, what risk we're able to tolerate. You know, he said yesterday, if, not if, but when. And zero, you know, zero, and that's part of our thing too, you know, only zero is acceptable. But, and a lot of folks, when we've talked about this, people will say, risk, you know, do we accept the risk? You know, we're accepting the risk. Tolerance is a significant word here. No risk is acceptable, but we have to tolerate some. Because a no-risk operation in general does not exist. So we have to say, well, you know, zero, obviously that is the ultimate goal. That would be where we'd want to be. But it's not a perfect world, so we have to determine, knowing that really that is a very difficult proposition, if not impossible, what are we willing to tolerate? So for ADM, for example, a few of our CSDs that we have in grain facilities. Carbon dioxide detection in our boot pits and tunnels. For those that have been involved in NFGA for a number of years, you might have heard about 8 years ago, we had a case at one of our facilities where we had wet corn coming in and it was emitting carbon dioxide, and it filled up the boot pit. Basically, it's heavier than air. And we had one of our colleagues go down. He was fine. He got out. We got him out. But we found out, we did a bunch of testing on the corn. We sent it into labs and our own research group, and we found that the corn was emitting quite a bit more than we thought. And so we installed carbon dioxide detection. And in the intervening years, we've had a few cases where we have had high levels of carbon dioxide that have shown up in our tunnels and pits. Not very many, though. But to this day, you know, we still have, in many cases, they're fixed. In a lot of cases, they're portables. But those are critical devices. If those are not functioning, we are not sending anybody into those areas. Is there carbon dioxide down there? Probably not. But we're not sending it down. It's a no-go. Nobody's going in there. Our grain dryer burner management, you know, Ed and Brian were talking about preventive maintenance yesterday, and I think Chuck and a couple others were talking about, you know, pre-harvest, post-harvest. Burner management systems, you know, when we have grain dryers, you know, are our Maxons working? Is the fire eye working? Is our purge cycle correct? And I'm not a burner management expert, but, you know, we have criteria on, you know, those get maintained, but they need to function. Does our temperature monitoring shut down the dryer? You know, do the protections that we have in place to protect propane or natural gas from leaking and causing a fire intact and functional? And again, if they're not, that's a no-go. I know probably a good portion, if not everybody in here, puts HAZMAT on items besides bucket elevators. But internally, we have a requirement that belt conveyors have hazard monitoring in addition to bucket elevators. So this is where, kind of now going into the middle a bit, but you know, on a belt conveyor, we require it. OSHA doesn't, but we do. And then air compressors and propane tank, pressure safety valves, pressure relief valves. You might not think about that much, but if you have propane tanks, do you have rupture discs? Do you have pressure relief valves on it? If you do they function? Have you checked them? There are ANSI, ASME standards on frequency of inspections of relief valves, of rupture discs. Do you do that? Do you have an air compressor? And in a lot of cases, you know, we'll have in a shop a relatively big air compressor. You might not think too much about that, but you know, if that relief rusts or plugs, do you ever pop that Kunkel valve or whatever on your compressor or your air receiver? those can blow, and I mean, they can blow catastrophically. So then there's also then kind of getting into the middle. For us, obviously bucket elevators, here's one where OSHA and us absolutely agree. Those have specific requirements for protection on them, and it's a no-go. It's a legal requirement. Also, we understand that that's a risky piece of equipment that must be protected. So I'm not going to read the whole standard here, but essentially what OSHA does require, to get back to the maintenance, is that not only with these, when we have legally required CSDs, not only are they in place and functional, but we have to maintain them. They need to be maintained. We have to have a schedule of maintenance, safety control equipment, dryers, like I said, magnets. Do you have magnets on your receiving areas? That's one where we actually have some variance in our risk tolerance within our own company. In some locations, we've put in pit magnets. We are so concerned about tramp metal getting into our process that not only do we have our 2.5-inch grates, we also put in our grate magnet to catch any ferrous. Then you have other locations, Now we don't have a corporate requirement for that, but so you could go to different ADM facilities and one would have it and one wouldn't, because there are certain locations where the superintendent said, I want it. But shutdown systems, alarms on bucket elevators, it's not just the sensor, it's also the control system that it goes into. What might be a self-contained unit like a couple of the presenters or the exhibitors have today, some that are self-contained and it just sends an output signal. In some, we have a lot that we wire into our, we've put into our own PLCs or distributed control systems and have to make sure that the logic is correct on that and that it functions. Bearings, filter collectors, these are all required by OSHA and mentioned in the appendix to guide us. And then you've got the company risk again. Which is based on the tolerance, which I'm going to show you our risk matrix, how we kind of try and quantify tolerance. And this won't be anything new. I'm sure everybody's seen risk matrices of in one format or another. Hierarchy of controls was mentioned yesterday. Obviously, the more you can either remove or engineer something out, the better. We do have some specifically identified items within our company in various procedures. For example, we require temperature sensors on pellet coolers on the exhaust. We require vibration detection on hammer mills. There's no particular regulatory requirement for those, but we've determined that we've had enough events in the past, learn from our mistakes, which we actually do sometimes, and have those as requirements. DHAs were mentioned, consensus standards, NFPA in Europe, ATEX, which is kind of the equivalent of our OSHA subpart S electrical with your area classification requirements, NFPA 70. So what I also meant to bring up, which is interesting for regulatory, I didn't have it in here, but I thought about it yesterday when there was the discussion of the authority having jurisdiction and the application of consensus standards regarding DHAs. Though not exactly a CSD, it has some parallels. We have a facility that we were doing some expansions and some work on. It's not a grain facility, it's a flour mill. And it's in a state where there is not a state statute or requirement to do DHAs. There's no federal requirement under OSHA. But when the authority having jurisdiction, the local fire marshal or the building official, I can't recall who, came in, the individual inspector said, I want to see your DHA. And then we're like, well, it's not required. There's no law, there's no regulation. I don't care. I want to see it. If you want me to sign off, I want to see it. So in some cases, you might get subjected to something like that where you might think, hey, I don't have a legal requirement. Sometimes it can be at the discretion of the official that is there. So just be mindful of that. Oh. Whoops. Okay. So this is our matrix that we have we have a few of these. It can be confusing internally, but this is our risk matrix that we use for our job safety analysis. So, but this is just to kind of give you a visual representation of how you might approach thought of trying to quantify risk tolerance. How do you quantify risk tolerance? You know, it was mentioned about it's very personal. You know, each person has a different level of tolerance, but how do you measure that? What's Jason's tolerance to this? What's Jess's tolerance to this? How do you measure it? So you try and quantify and use a matrix and try and at least get a little bit of a quantification to it. So this matrix, what risk is, I guess the definition in general is it's when a hazard that exists, here's a 2-foot fall hazard exists in front of me. And then the likelihood, how frequently or how likely is it that hazard could come to a point where I suffer a consequence from it. And so the risk is where those coincide together. And, you know, so hazards don't always turn into a consequence, but they're always there. The risk is the likelihood that they do come to fruition. So like here, when I talk about no-go, on this, though it's not equipment-specific related, this would be, you know, when our folks are filling out a JSA, they would say, okay, if I think that this could be a permanent disability, injury, and it's pretty likely. It's a 9, you know, it could happen occasionally. So now it's a 9, and then we escalate who needs to approve. You know, if it's in the green, go ahead. If it's not, we need to have discussions. We have similar matrices for our process hazard analyses were mentioned yesterday by Tim. You know, we have a lot of PSM chemicals, and we do a lot of PHAs, process hazard analysis. We use hazard and operability studies. And we have another matrix there too, like could it cause death off-site? Could it cause death on-site? You know, and what's the likelihood? And then you try and quantify it. Different matrix, but similar application. The point of these is to set up what is your company's risk tolerance. This is not an OSHA regulation. Those severity on the injuries, that was determined by us. What level of injury and at what frequency are we willing to tolerate? We're not willing to accept an injury, but what risk are we willing to tolerate to operate? So, again, it's personal. There's, you know, I've probably heard it a million times, there's some people that are comfortable jumping out of airplanes with a parachute on. There are some people that won't even get on an airplane. So that's a big range of what a particular individual's risk tolerance is based on, who knows, personality, experience, life experiences, education, whatever it is. So one thing too is that tolerance for voluntary risk is often much higher than involuntary risk. When I think Scott yesterday was talking about the blue line, you know, if you're doing it, you're driving the car. You know, there's some people that don't like to be in a car if they're not driving. I'm in control. You know, I'm voluntarily taking this as opposed to sitting in the back seat and I've got to rely on this goofball to drive me around and I don't trust him. If you feel like it's voluntary, often people will accept much higher risk than if you think it's not. And tolerance also changes based on the actual consequence that could come, regardless of how likely it is. So, high consequence, a plane crash. I just heard the other day that in the US, I think that there's only been 2 airline incidents that have been investigated by the NTSB in the last 10 years. And there's been like 100 million flights. So the probability of anything happening on an airplane is very low. But me, when I'm on a plane, when it hits the turbulence, I white knuckle it and I always look at the flight attendant and see how they're reacting. Okay, all right. She's still serving drinks. It's all fine. But what's the odds? They're very low. But if it goes down, it's bad. You know, Indiana Jones jumps out of the plane and pulls the thing and an inflatable raft comes, they don't give you that on the plane, on a 737. But then low consequence but high tolerance would be driving again. We do that every day. Most people don't think twice about it. It's more dangerous. We all hear that statistically it's more dangerous. But people seem to have, the risk tolerance is less, they have less tolerance when they perceive at least, or maybe it's reality, of an extremely high consequence. But a good example of this in a way is if you ever heard of the Deepwater Horizon, that oil derrick. I don't remember all the circumstances, but they had an explosion, killed a whole bunch of people. It was terrible. It was out, oil derrick out in the ocean. And right before that, they'd had a celebration for however many days of, no recordable injuries. No recordable injuries. So great. And then it explodes and kills people. So at any rate, what happens when that low probability but high consequence occurs? I don't know where this occurred, but in this case, it appears that it started in the bucket elevator. And again, going back to the very beginning, my simple mind, what do you have in place? What do we have in place to stop this? Even if you don't have safety devices on your bucket, if you just run that, you pull all your hazmat off, you take the green washer bolts and you just put grade 8 bolts in all your vent panels and let her go. It's probably not going to blow up, but you're playing with fire, figuratively and could be literally. But in this case, there's a couple of things that, not knowing the circumstances, but we've also had them unfortunately internally where we've had some bucket elevators go, and in retrospect, you look at it, if that hazmat, if that CSD had worked, because we didn't do whatever, and it was our fault, whatever we did or didn't do, it would have stopped that. All other things being equal, bad housekeeping, poor maintenance on the bearings, belt not tracking, whatever it is. If that alignment sensor functioned, if we had maintained that correctly, I'm just being hypothetical here, that would have stopped it. So CSDs fall under a whole variety. Yesterday you talked about acts, systems. So if you think about layers of protection, that Swiss cheese that's blocking the hazard from becoming that consequence, you're reducing the likelihood. How do we reduce the likelihood? The hazard's always there. Combustible dust is there, it will explode. That's a hazard. How do we cut that likelihood to a tolerable level? There's a number of variety of controls that we might have in place, many of which could be CSDs. That's the same definition again. But ideally, here's kind of a different way of looking at the layers of protection. Inherently safe design. Can we design it so there's no dust? Maybe not. Then you get into systems, basic process control systems. Does our PLC function? Are the set points of temperatures or speed set correctly? Is it programmed correctly? Is it tested? Various instrumentation and alarms, maybe you have a separate system that's a more highly reliable system. You might have heard the term SIL, safety integrity level, higher reliability of a system because you feel that this is more, this is important. We don't have that level of tolerance. You might put in something that's more reliable. Safety instrumented systems, engineering controls, and then we get in, active engineering controls, that might be something like your explosion suppression system on your leg. It requires a sensor to pick up optical or pressure or some other input, and then it sends a signal and it releases extinguishing material into an area. It requires electricity, it requires monitoring, it requires control logic, it requires a number of things. Sensors, control logic and problem solving in the system, and then actuating. Passive engineering systems, venting, things that we don't generally have to have that kind of level of involvement in. And then finally, emergency response. What happens if it does hit the fan? And maybe you've seen a bow tie model before, but so going back to the if, not when. I'm sorry, when, not if. In this case, The bow tie model is, if you think about, and in this case, the critical safety devices can be on both sides of the spectrum. I view this, though, as when he talked about when, not if. The when is the event in the middle. So I agree with him and I disagree in a way. What you have here is, on the left side, you have preventive measures, engineered processes, control systems, human intervention, operator procedures, and interventions. Those all fail. You have that bucket, or you have that grain elevator just exploded because the HAZMON didn't work, our preventive maintenance and housekeeping programs failed, whatever else. We have an explosion. Okay, so that's terrible. But again, going back to the crane, how do you mitigate that if it does happen? So again, you could have engineered solutions. For example, maybe you have the control room down the road, or have a blast rated enclosure that would be able to withstand whatever happens. Maybe you have venting that goes to a safe location. Maybe you have good response procedures, like the Formula One race car that happened, that event that was in that video. So if the preventive measures fail, you can have an event. Nobody's hurt yet, maybe. If you have mitigation systems in place, then you would prevent the injury, you'd hope. If all those fail, you can then have that ultimate consequence. So in many cases, your CSD, I think a lot of time, I know I tend to lean toward thinking about critical safety devices as things that prevent the bucket elevator from going. And of course, I prefer that. But there can be, on the other end of it, where even if something bad happens, we have devices, safety processes in place to prevent people from being injured. So I'm going to jump through this real quick, but I don't know. Maybe you have gasoline at your facility. Maybe some co-ops you maybe have gas stations. At one of our facilities, we have a number of facilities that do hexane extraction, and we might have hexane come in or out of the location. So say there's a delivery, the gas releases, there's some sort of a problem. What's the worst case scenario? There's a truck right there with a driver in it, and he or she is offloading or loading tanks. It has a release. The worst consequence that could happen, nothing's happened at this point, but there could be an explosion, it could be a fire, it could be maybe that person gets killed. Maybe there's a significant cost if you have damage to the property, the equipment, interruption. Maybe there's an environmental or facility impact. We had a case a number of years ago at one of our oilseeds facilities where we had a third party come in. We were converting a boiler from fuel oil to natural gas. And we had a truck come in very similar to this, and he was going to pump off the fuel oil, number 2 diesel or whatever it is, basically. And number 2 fuel oil. And they were pumping it into the truck, and he didn't bond the truck. And there had been gasoline in it before, and there were vapors, and it had a static ignition. I saw this video, too. It was horrific. And boom, fireball comes out of the top, burned him. He runs off the truck. He's on fire. One of our guys comes out, knocks him down, hits him with a fire extinguisher, and he passed away like 2 weeks later. It's horrible. So in our hexane processes, we have pumps interlocked with bonding and grounding cables, where if you pull a truck up with hexane, you can't turn the pump on until you connect the bond to the truck. You connect it over to the grounding bar here. There's a logic system. Now it gives the permission for the pump to run for that type of a reason. But so in this case, we have offloading. They don't have bonding. And so our layer of protection in this case might just be a single one of, hey, just stand away from the truck when you're filling it or whatever. And that would stop it. But if we have things, we have unloading practices. We have maybe a high-level switch on the tank so it won't overflow. And those should work. But say they don't work. Say you don't maintain the high-level switch or high-level indicator. And the SOP, I'm sure it happens at our location, probably none of yours. Sometimes people don't follow the procedures correctly. So they don't. Now we've got a leak. Now it could be releasing vapor. So that's your preventive side, and those have failed. Our event now is we've lost containment, flammable liquid. So what do we have to prevent something bad from happening? We have a secondary containment, we have a berm. Maybe we have gas detection in a sprinkler system or a deluge in place. If those fail, then you could have a fire, you could have an explosion. So do we understand what could go wrong? Are we tolerating that risk? What are our CSDs in this process? Have we identified? Have we said, you know what, in this case, and maybe you have something similar, and I don't know if you thought about it or not, is that high-level indicator on that tank critical? Is that bonding wire that prevents the pump from running when you're moving flammable liquids critical? And again, it goes back to your tolerance. It goes back to what you think. For me, yes. How do we know that they're all working correctly? So here's an example of a bow tie for a dust explosion in a bucket elevator. And I apologize for the small writing. But so, standard bucket elevator here. How would we, how would we in a perfect world mitigate that consequence from occurring or prevent that consequence from occurring? So on the preventive side, hey, maybe ideally we can move that bucket elevator and that bin, 100 yards away, so even if something goes wrong, nobody's anywhere near it. That's the design part. Outside of occupied areas. Don't answer now, but do you have any places where you got a control room right in the middle of your grain elevator and maybe there's a bucket elevator running up behind the chair where the person sits that grabs samples and does grading or whatever? Design, maybe we do slow speed. Talked about bearings yesterday. Maybe we put a cool device on our bearing that measures ultrasonics and vibration at once. Get Ed in there. But maybe we run it at slow speed, less than, NFPA 61, 500 feet per minute, for example, is in the annex. Maybe we just, hey, can we run it slower? Less friction. That's a design. Control systems. Does our PLC monitor it? Does our PLC, and will it have appropriate reaction if it detects a situation or a circumstance that we don't want? Preventive maintenance and housekeeping programs, systematic. Keep the dust away, again, off the equipment, so even if it does go, there won't be a secondary. And then instrumentation and alarms, our hazard monitoring, operator intervention. At a 90% speed, does it alarm and do you have your operator intervene? At 80%, does it interlock, shut down, no questions, done. If those all fail, and some of these might be what you would consider at your location based on your tolerance, a CSD. Obviously the HAZMON, at least the speed and the alignment, if you're over 1 million bushels and all that, that's a regulatory requirement. That's a CSD. Say you're not though. Say you don't, say it's an outside bucket elevator, and OSHA says you don't have to have it. We would still have it. I assume most in here would still have it. So it would still be something that we would consider, that's critical. If that speed sensor goes down, we're not running. Done. Until we get that fixed. Inside, outside, 1 million bushels, less than 1 million bushels, whatever. Then on the mitigation side, so all those fail, we have an explosion like that video showed. What are our controls? Well, in some ways you might think that if the possible ignition could be a bearing is heating up and the HAZMON does intervene, the interlock does work, in some ways it's preventive and mitigative, shut it down. Suppression and isolation. You have an ignition, you have a pressure rise. It intervenes and it mitigates it, prevents it from blowing the whole place to kingdom come. Passive controls. You have vents that shoot it off to a safe area, but it does happen. Again, blast resistant. And evacuation procedures. Is everybody milling around, or do they know where to go? Do we know how to efficiently get people to safe areas? If not, if all that fails, then we could have explosions and injuries. So preventive CSDs, HAZMON, PLCs, AMP detection maybe. Then on the mitigation, interlock suppression, blah, blah, blah. This is a whole lot of words, and I'm not going to spend a whole lot of time on these, but essentially, I'd say that when I get back to the whole pornography slide and that, what's subjective, we have some locations say, well, every single interlock we have, every single sensor we have, that's critical, isn't it? Every one. If everyone is critical, then none are, right? Then on the flip side, you might say, we don't have any. I mean, we're fine. Everything's good. There's a happy medium, and where is that? And we struggle with that. So not every sensor, not every device is. Again, going back to try and keep it simple. What will stop it? If there's any one thing, is there one thing or two things that would stop that from happening? Those are the critical ones. So internally, we have to identify those. We report out on them. We have to identify inspection, testing, preventive maintenance, report that we're doing it, how many were scheduled, how many were done. And again, this is a whole lot. But here's just some ideas. What are things that we, within ADM, not just grain, of course, consider CSDs? Anything that we identify in a process hazard analysis as being necessary to prevent something in our risk matrix from being in the red. And that oftentimes is not a legal requirement at all. We determine we need this sensor, we need that input, we need this. That's critical. You identify that, you location that just did that HAZOP, you identify that as a critical device on your inventory. Pressure relief valves, steam, compressed air, any compressed gases. Gas detection systems, our carbon dioxide sensors that I mentioned. Smoke and fire detection. Process alarms, if we're requiring that alarm to have a person do an intervention to stop something. So not all alarms. And maybe we suffer from this, and maybe others do, of way too many alarms. You have an operator sit down, and there's 50 alarms up. Which one matters? That's the critical device. That's the CSD, that alarm. This one's nuisance. That's a problem. But UPS systems, what happens if you lose communication on your HAZMON? We've had that happen. We've had it lose communication and freeze in the current state that it's in. Our bearings are at 90 Fahrenheit. Lose communication. 3 hours later, 90 Fahrenheit. Even if they went to glowing hot. Do we have UPS? Do we have backups? Emergency shutdown systems, pressure systems, spark detection, fire suppression, sprinkler systems, burner management systems, interlocks that take the process to a safe state without intervention. Not necessarily an operational good state, a safe state. The speed sensor shuts it down, it's not gonna blow up. Temperature sensing, this is a lot of the same thing, but plug, choke sensors, vibration sensors, suppression systems, high-level sensors in tanks, PRVs, PSVs, emergency alarms, DP on bag houses, cathodic protection. Has anybody here ever had a gas line corrode under the ground and then you get gas? We've had that, where we have folks walking by, going to the office, I smell gas, and we found out that the buried line, the cathodic protection failed. We haven't pressure checked it, and now we've got gas just coming. And this is just an example here of one of ADM's lists of here's minimum CSDs. This isn't all inclusive, but this is at a flour mill. So we'll have, what's the process? A fire explosion and dust collector. So our critical devices are venting, pressure sensor, an optical sensor. Those are part of the isolation system. Actuation and isolation valve, extinguishing media, dirty air fan, bearing temperatures. Chlorine system, we have chlorine in some of our mills. Detection, automatic shutdown. Explosion suppression systems, HAZMON on bucket elevators, on belt conveyors like I mentioned earlier. Hammer mill vibration sensors and other things. So, to go back to the go, no-go. What do you do if it's not functioning? What do you do if you have a CSD? You have a bucket elevator, the speed sensor stops functioning. Well, that's a regulatory requirement for one. If it's regulatory, you need to shut it down. And if you're doing it based on your risk tolerance, what is your risk tolerance? If you've determined that this is critical and it's not working, what do? Should be shutting it down or else have a pretty darn good reason why you're not. So we do sometimes allow some equipment to operate. We use a permit system. We'll do like stepped up inspections. We call it an impairment. It requires multi-levels of approval and a very clear time frame, very clear corrective actions that'll be put in place, and what testing and inspections we'll do during that. So think about that. If you've identified it, we need to maintain it and they need to function. So here's just a few events that have happened in our location. I mentioned the pellet cooler and the temperature. The events like this are why we require temperature on exhaust. We've had, maybe it doesn't do it justice, but a significant catastrophic pellet cooler coming in a feed plant. the pellets getting too hot, going into the, getting stagnant in the cooler, and not checking the outlet temperature, and eventually it results in a big fire. Propane vaporizers at a grain dryer. We weren't doing our preseason checks. We weren't checking the safeties on it. Now, fortunately, this gets into the mitigative part of the bow tie. This is away from the facility. It's away from anything, so nobody was hurt. But it was a huge fire. This was a grain dryer that we had on the left in Indiana a couple years ago. Management of change was mentioned. That's kind of an aside, but the circumstances on this was, if we switch from liquefied petroleum to compressed natural gas or liquefied natural gas, we can get you guys a better deal. And we've got this regulator that we can hook up onto your line and it'll work perfectly. And it did. Perfectly burned our grain dryer to the ground. So management have changed. Outside of CSDs, but also they change it, and now you've got your burner management system set up for one fuel, and it's a different fuel. In a flour mill, this is an impact mill, high rotation equipment. We require bearing sensors on these on the rotor. This one didn't have it, and it resulted in, this really doesn't do it justice. It burned up a number of the equipment and floors above it as the bearing got hot, high rotation speed. This was a bucket elevator that we had that exploded. It blew the panels out. You can see the bonnet on the top in the middle. That on the left is a vent panel, blew out all the vent panels. And on the right is the boot in the pit. Now this location had very good housekeeping, very good. And there was little damage aside from this leg. But this was a new acquisition. They did not have Hazmon, and during COVID, we couldn't get PLCs. The microchip shortage. Everybody was mining Bitcoin. So we couldn't get our panels, and we had it on order, and this happened like 2 weeks before we put Hazmon in. Another bucket elevator. Look at that bearing in the shaft in the middle. You can see on the right it ate out the bearing housing. Hazmon didn't work. You can see on the left that there is Hazmon on the bearings. Didn't work. Temperature cables. I don't know, maybe you don't think about temperature cables as something that's critical. In some cases, they probably should be. Here's a case inside one of a bin that we have, and this bin eventually did catch on fire. As you can see on the right, we had to cut a hole out, and this took, if you've ever been involved in something like this, it takes months to handle it. But you can see how, and obviously huge potential hazards, not just from the event itself, it's ongoing in the response. Our Deere temperature cables work. Do you test them? Are the temperature cables themselves leaking water and you got water going down the cable and causing the problem? Do you have venting on your dust collectors? On the left we had a dust collector before and then a nice one after with venting. It's hard to, this photo doesn't exactly do it justice, but it did tear it open and then it caught on fire. Nobody was hurt. Here's an air receiver tank. This is an ADM, but I found this on I think CSB video. You can see that 200-gallon tank or whatever, blew that whole building out. You can see on the right, just devastated it. This was at a facility we have in Europe, commissioning a steam system. Hot commissioning, run the steam in it. We just put all the piping in. Water hammer, you can see on the left, it blew the pipe out and it just ruptured the panels on the walls. So maybe you don't have high pressure steam, but it doesn't take much. 50 pounds per square inch, how many square inches is the inside of this? A lot, thousands of pounds. So I'm not gonna get too much into maintenance, but it is key that those function. We've identified them as critical, and they need to function. So, I never got, Brian Knapp's not here. I asked Brian to use 4B images, and he said it should be okay, and he'd get me a letter, and he never did. So I hope there's no lawyers in here, but I did use his images. However, when you have them in place, they need to be checked. I know yesterday that there was talk about 6-month checks. We do quarterly checks, visual, for things like placement. We do 6-month speed testing. I'm not telling you to do this. We do 6-month speed function testing, and we do annual freeze spray to just check and make sure that display is correct, it's the correct bearing is displaying on the HMI correctly and whatnot. So we have, this is actually out of our DHA sheet for bucket elevators. We talked about checklists yesterday. We have a checklist for that we used. And we identified on here, here are our CSDs, and here are our nice-to-haves. So, the important thing, though, is you establish a frequency. I would highly recommend you do at a minimum what the manufacturer says, unless you have good reason and good documentation not to. But set a frequency, stick to it, and document it. Anybody that's ever been involved in any event or inspection that has involved with these, somebody mentioned yesterday about electronic records and how it was at their fingertips when OSHA came in. I mean, that's when it matters. The documentation might not matter that much to you now. You throw in a banker's box, it goes in the basement. But if something happens, or if an inspector comes and they want something, it matters then. And I've been through enough of them that, boy, it's nice to be able to just have them at your fingertips. So, when you're looking at it, sensor placement, rub blocks, this is why we do quarterly visuals. We see this, unfortunately, quite often. You get slow, infrequent rubs, and it'll cut a groove right into that rub block. So, visually inspect it. Is the rub block intact? You're not necessarily checking the sensor itself, but lock it out, do it safely, open it up, take a look at it. What condition is it in? On the right, this is a creative, we had some tracking problems, and the touch switch kept shutting down, kept alarming. So this is the blue line and the whatever line coming up. I hate to be a jerk. So, you know what we should do? We should go to the shop, find some channel, find a pulley somewhere, bring it to the drill press, thread a pulley on it, go up there, drill holes in the floor, bolt it on, cut a hole in the head, and shove the pulley in there so the belt won't come over. My goodness. Maybe I'm a simple person. Wouldn't it be easier to fix the tracking? But anyway. So we've gone through, when we put in HAZMON systems, it was mentioned yesterday that some folks are doing their own, one of the panel members. We have an internal group, too, that also installs HAZMON, and we have a pretty extensive checklist on commissioning. Because we had problems years ago where we'd put these in, we'd go out, we spend tons of millions and millions of dollars to put these in, and then you find that they didn't password protect it, so people can just go in and acknowledge and disable that alarm that's bugging them in one of our facilities and then blow it up the next day, which actually happened. If we lose communication, you pull the cord, does it keep reading static temperatures? That happened. So we have this whole commissioning process on making sure that it functions as we say before we hand it over. Operations, elevator superintendent, here you go. Here's the sheet. We've checked all these parameters, and it's good to go. Suppression systems. May have these. This is, here we've got hammer mill, we've got a conveyor. There's flameless venting, isolation and suppression, mechanical isolation, venting. We lean toward where we can, anything passive. Mechanical isolation valve, just preference. Venting as opposed to chemical isolation, chemical suppression, but they're all good. Where do you place them? Common spots. What's important on these, I'm assuming nobody here actually designs their own suppression systems, but if you do, or if you have somebody do it, don't accept them just putting it. You want to have, going back to the documentation, you want to have that design document in hand, the drawing, where they're supposed to be placed, how many feet from the bonnet on the discharge can that bottle be, whatever it is. You want to have that in hand and keep it, and don't lose it, and don't throw it in the banker's box in the basement, and then the river floods, and then it washes that all away, and then you never have it again. Hypothetically. For suppression, what we do is weekly checks. But something that I did want to call out here, and again, I know it's not regulatory, it's consensus standard, as we've talked about, But in NFPA 69, which is the suppression standard that NFPA 61 and 652 refer to, it does specify that inspections of suppression systems are done every 3 months. And most manufacturers, in fact, I don't know of any, at a minimum require that their folks come in at least once a year. And OSHA will enforce that, hypothetically. I don't want to call it out, but you may recognize this. This is my last slide, but why are they important? I brought up differential pressures before on dust collectors. Is it a critical safety test? I don't know. OSHA tells us to do it. Is it that big of a deal? Maybe it is, maybe it isn't. But there was a significant explosion at this facility, killed a few people. And the owner, I think it was a quality manager, safety manager, they falsified dust collector maintenance records and cleaning records, including the differential pressure. They had an explosion, people get killed, and these people are in prison, or will be. They just were convicted. I think 2 brothers that own it and a couple of others, I mean, they're going to prison, as far as I know. So they were referred for criminal prosecution. So at any rate, so in this case, was the differential pressure detection system, monitoring system, a critical safety device? They will have time to think about that in prison. So with that, I think I've come to the end, and this has stopped working, so that's timely. I know I only have a couple minutes.
Yeah, thank you. Great presentation, Jason. Yeah, we have just a minute or two. Any questions, comments? All right, well, thank you very much, Jason. Great job. Thank you.